Right. Okay. We are live. Welcome everyone to another episode of GPU Mode. Today I'm really thrilled to have Lanxiang Hu from the How Lab at UCSD, who's going to be talking to us about something pretty different today, which is his project around the LM Game Bench, which is evaluating LMs through computer games. While this isn't like, I guess, like the typical making GPUs faster kind of talk, a lot of these topics I think are very relevant for people to think of in general if you're in ML systems. So yeah, I can't wait for it. So thank you, Lanxiang, and please take it from here.
Thank you. Thank you so much for the kind introduction, Mark. Hi, everyone. My name is Lanxiang Hu. I'm a second-year PhD student from UCSD. I'm working on efficiency problems for large-scale machine learning workload, as well as we're trying to bring new perspective to AI model evaluation. So today we're going to share our recent work on how to evaluate and training LLMs on games, and why we think gaming environments are important. So over the past few months, we have been working on recycling a lot of the conventional, very classic gaming environments and use them for AI evaluation. And we have actually some pretty interesting results I want to show today. Maybe we can first start with a few demo, and we can take a look at why we use gaming environment to do evaluation and some lessons learned along the way. Okay, let me share screen. Yeah, so this is an example where we use the Mario game. I think everybody's quite familiar to do a side-by-side comparison among different models. Okay, so as you can see, Call 3.7 won the game, and so this evaluation was done in March during the time. So that was the state of our models we have at the time of evaluation. So you can see actually when it was in February and March, when those models were with their people, the assumptions are the models are still very good at a lot of math and coding reasoning tasks, but that was also the time that agentic evaluation starts to pop up. A lot of the agentic evaluation are just get used. Computer use agentic evaluation to use agentic evaluation, but there hasn't been work on evaluating the models on the gaming environments. So games are very intuitive and relatively easy tasks for humans. So we all play games when we were young, but how about the models? What if we put the models in the gaming environment? Actually, this is pretty surprising, right? You can see like GPT-4o just game over straight away when we put it in the game, and Cloud 3.4 and Cloud 3.7 they didn't last long. Neither. They were good. They were better than Gemini 1.5, but you can still see there was a very big gap. Okay, so let's go back to the slides. And then it brings up to the questions, if we goes to a higher level, why do we work on games? So back in the time when those agentic models starts to pop up, when people start to use reinforcement learning to train on LLMs, we start thinking about the questions like before the era of LLMs, right? There were a lot of environments people use for RL trainings, but not on LLMs, on those conventional RL agents, like deep Q learning and stuff. So in the good old days, people use gaming environment a lot. For example, there's this repo called OpenAI Gymnasium and OpenAI like Stable Retro, where they recycle a lot of the conventional game, classic games, popular classic games, and they the advantage of those gaming environments are they have very well defined states, actions, and verifiable rewards, right? And this way you can easily calculate the rewards for your rollout, the advantage for different rollouts, and this way to train the models. And also, very importantly, there are just a tons of games that are there, and they're popular. People are familiar with it. People know how they work. People know what their rewards are. So it's very easy to scale. There's just so many gaming environments. So building up on this motivation, we start thinking about the question of why don't we just use those environments first do benchmarking to see how they perform. And along the way, we found just putting the games in the gaming environment actually doesn't work well. It doesn't provide meaningful evaluation. And that's why it needs this, what we call harness design. We'll go into a little bit deeper later. And with harness design or with agentic workflow, how do we do evaluation is the final question. So the first question, and I think the biggest question, a very important one, is how do we choose games? So we actually, it was actually harder than we thought, because the games has to be of moderate difficulty levels across different LMs. For example, if we put all the LMs into League of Legends, right, they won't be able to play. Or like Dota 2, they won't be able to play because they're just too difficult for the models right now. They don't have a very good physical sense. And also, another important question is we want to have diverse enough game types. So the difficulty levels need to be moderate, and also the game types need to be very diverse. And we also want to use common games or popular games such that the results are very interpretable, are very understandable. For not only the AI researcher, but also for the general audience. So we choose games across a few different genres. This was during the time we wrote the paper about in May. So we have a few puzzle-solving board games, like Sokoban 2048, Candy Crush, Tetris. Those are obviously people are very familiar with. And for some games like Sokoban and 2048, they require more of long horizon planning because you have to push the box and leave space for later. This way to make sure all the boxes are anchored at the dock. And also for 2048, you want to make sure your hard numbers tiles, they stay in certain corners, right? You need to plan your space strategically. For Candy Crush and Tetris, actually, they require a lot of spatial reasoning, especially for Tetris. You have to rotate your Tetris pieces correctly and to place them into correct positions. This is actually very hard. We didn't see the models to get to steadily clear lines until O3 Pro came out. Actually, O3 Pro and Grok 4, they actually did pretty well on it. If people are interested, you can go onto our YouTube channels, LM Game YouTube channels. We have a few videos on how the models they were able to clear games. And we also have some real-time like motion games, Super Mario Bros. And we also have visual novels, the games where it's more text heavy. It's like a detective style game. So you need to solve a detective puzzle along the way when you're interacting with a lot of different characters. And people usually call this kind of genre visual novels. And this is the game Ace Attorney, which was also a very popular game. Okay, so then with those gaming environments, if we just put the LMs out of the box, just put them in the gaming environments, actually, they just aren't able to get a good performance. Why? Mainly because of three reasons. The first one is it has a very weak vision perception capability. We can show a demo later about how the models get confused. And the second one is a lot of the models, especially reasoning ones, they have super long latency, right? So depending on how you build agents or how you do evaluations, if you use computer control style agents and let the model control your keyboard and have the gaming environment run as a parallel process, the latency is just too long. Maybe after two responses, the Super Mario timeout, has already timed out. The game has already over. And the third one is many times the models just make repetitive mistakes. They make the same mistake again and again because they don't have memory, right? That's a common issue for LMs. They don't have a memory mechanism. So that's why, in order to distinguish the model capability well, actually, evaluating models with gaming environment require an agentic workflow, and we call that's what we call gaming harness, and we design actually a modular gaming harness in a modular way. This way we can study how different components how different components contribute to model game playing performance. So when it comes to harness design, we have three major components. The first one is vision perception modules. So the vision perception module is where is to tackle the weak vision perception issue, because the vision perception module, they convert image to text. They either read game state from the backend or query another VLM to convert image elements into textual descriptions, right? For example, if you have a Sokoban game, you have the box pushing game, and if the models, if it's just provided with the image, sometimes models just get confused. They recognize a wall as the box, or they recognize another box as the wall, right? They have this perception issue. But if we read the game state from the backends to provide it with the ground truth, or ask another the latest, the strongest VLM to extract the elements, it can mitigate the perception issue. The other module is memory module. This module is well recognized important components for agents, especially in games, because let's also take Sokoban as an example. If it doesn't have a memory, imagine it doesn't have a memory. For human, we usually make a plan about, say, okay, I have the two boxes in front of me. I want to first push the box A to a certain location, and then I want to come back and deal with box B, right? We have this kind of long horizon planning. But for LMs, we observe they actually don't. We need to design this memory mechanisms to prevent it from very hesitant decision making, because otherwise it would just jumping back and forth between box A and box B. It doesn't know how to proceed the next. It doesn't have this long horizon planning. But if we record its gameplay history, we tell, okay, in the next move, in the previous move, you already decided to deal with box A first. Then it knows better. Then it has a more consistent planning. The third modules we introduce is reasoning modules. So this one basically integrates all the information from vision perception and memory modules to synthesize all the information it has. The outcome would be to generate an actions. And there's a choice about either to turning on or off the long chain of thoughts reasoning mode. And here's a schematic overview of how we design the benchmark. We first design all the game environments as with gym style API. It's an observation space, action space, and also the game states represented in either a textual, like a tabular representation, or just an image, right? So the game state will be fed into the models. The model can selectively turn on the agentic components, the scaffolding component, right? This memory module or perception modules. Um, and they will generate an action. The action will be then fed into the gaming environments to drive the state change, and the next states will be generated, and this keeps going and going. So then it becomes the question, how do we do evaluation in different games? In the board games, like grid games, we found LMs, the biggest bottlenecks are biggest bottleneck is LM struggle with game state understanding if we just provide it with an image. So we actually prepare them with certain with textual format, because in the board games we can also represent represent the game states with textual formats like 2D ASIC2 table, right, or object list. You just have a list where to tell the model the block is at a certain coordinate, the player has a certain coordinate, and you enumerate all the coordinates. You tell where is where. And for real-time games, the challenges are different. The challenges are because those games, they are very latency sensitive. We need to specify what whenever the models take an action, how many frames it changes, right? Let's say the LM execute an action, say jump, and then we need to the model also needs we also need to specify how many frames it corresponds to with that action. That corresponds to, like, imagine you're playing a Super Mario game with a joystick. Sometimes you also hold different keys for different amount of time, right? So we want to map this behavior to action taking as well. So you can see we dictate it to generate in a format like jump 10. That means like press the jumping key for 10 frames. And also we observe an interesting phenomenon, what we call the knowing and doing gap. For example, in many cases, the LMs actually get a very sensible planning in natural language. Let's take a look at this example. Right, it's able to reason it's able to make a very reasonable plan. Like in its reasoning process, in its reasoning trace, it says to safely navigate the pipe, Mario should maintain the momentum and height. However, when it comes to execution, many models aren't able to map this kind of planning to the exact actions, like control different keys to very exact frames. So that's an issue. And also, there's a low frame per second issue, because the LMs are only receive the state changes, the new states, after actions finishes, right? So if it doesn't provide it with a memory mechanisms when the Mario is in the air, it doesn't tell if what's its momentum is, and what's its so basically what is its trajectory in motion. In other words, the game states inputs are too sparse. So that's why we also need the game state mechanism. And the other genre is this detective games. I think it's very interesting because it's a very different genre. Ace Attorney is a text-based courtroom games, right? So you first interact with different characters to get to know your court case, and then you collect different evidence. Then you go to the courtrooms. The judge asks you different questions. You confront with other people's, and you want to present your evidence strategically in order to justify your court case, to solve the case, right? In those kind of games, the challenges is actually data contamination issues, because those games are text heavy, and during LM pre-training, chances are a lot of the game information has already been exposed in the game forum, so they are part of the pre-training. We run a small experiment to test the data contamination in this kind of games. For example, like in this case, we asked the models the same questions about what's the plot in round one, right? And we found the all three models' generation output are actually basically exactly the same as with the Wikipedia text. So there's a very severe memorization issue. Basically, before the model gets to know any of the plot, it's already able to generate, it's already able to record the entire plot. And we run this experiment about, so now we see there's a memorization issue. Does the memorization issue actually translate into gaming performance? We run this correlation study, and we see the red line is where it shows there's a strong correlation between the memorization and your gaming performance, right? So on the x-axis, it's total similarity. So how we do this is we employ sentence BERT models to compare your ground truths with the LM's generation, sentence by sentence, and then you can have a similarity score that quantifies your memorization, how well the model, the memorization severity, right? And then you also have this rank. The reason why this rank is negative slope is because lower rank means higher performance, right? Because like, let's say you perform the best, then usually your rank is number 1. If you perform second of the best, your rank is number 2. And so that's a very big issue for this kind of games. In order to mitigate this data contamination issues, we employ several methods. First of all, we do an entity replacement. Basically, we replace the explicit name in the games. Let's say attorney Phoenix Wright with just attorney A, and with evidence, certain specific evidence with, say, evidence 1, evidence 2, those generic names. Also in the prompt, we explicitly instruct the models to do reasoning over memorization. The other is before we conduct evaluation, we rewrite the background context, the game, in-game text with in a different way. We reward it. So after all this mitigation strategy are applied, you can see the curve now becomes the blue one, where there's a still memorization going on, but it's less correlated with your gaming performance, and suggesting a reduction of induction in the memorization effect in affecting gaming performance. And okay, so after mentioning how like different games, they place different challenges, right? And that's why we introduced the gaming harness. And after introducing the gaming harness, does it work? We conduct this harness effectiveness evaluation. In other words, we compare the model gaming performance before and after you apply all the gaming harness. You can see the delta is actually pretty significant, especially if you look at percentage delta. In other words, what's the percentage model improvement before and after applying the gaming harness in comparison with the baseline. So you can see if we do a statistical hypothesis test on whether it's significant to whether the performance improvement is significant, you can see the p-values are large. And the exception is Super Mario Bros. Because in Super Mario, it's a partially observable games. It's kind of sarcastic, and it's harder. For a lot of the model, they still don't have a good physical sense about how long to press each key. So even applying the harness, the randomness is still huge. The gaming performance variance is still large. It's not statistically strong enough to say, okay, the harness resolve all the question. Okay, and then so after we come up with all the games and design addressing the questions, the data contamination issues by adding the gaming harness, we have leaderboard, and the leaderboards are twofold. It has this model leaderboard where we don't apply any harness, and we also have this agentic leaderboard where we apply all the harness. So I can show a bit about what's the status of the leaderboard right now. Yeah, so we welcome everyone to check out our leaderboard. So it has two components, right? The first one is your model leaderboard. You can do a side-by-side comparison, see how normalized score compare among all different models across the 6 games we provide. Currently, O3 model is still the best. O3 Pro actually performs better. But O3 Pro, the cost is huge. It's still huge. We're unable to do end-to-end evaluation across 3 runs. So for all those metrics we report, we run the models on the game 3 times, and we calculate the mean, the variance. For O3 Pro, we aren't able to do it yet. The agentic leaderboard, we apply all the gaming hardness. O3 is still the best, and Gemini 2.50 Pro basically follows. Okay, let's go back to the slides. Okay, so the first goal is the benchmarking. And after benchmarking, the second important goal is, okay, now we have all those evaluation results. We have the good leaderboard. How do we understand the gaming performance, right? We have, so in other words, an important question we think is, what does good gaming performance mean? If you have a model that performs well on gaming environments, if the models are trained on the gaming environments, what does it mean? So we study from those two perspectives. In the first perspective, we want to study the relationship between gaming benchmark or your gaming performance with other benchmark, with other existing benchmark. So if we compare Geekbench's results on different games, on Sokoban Tetris 2048, they each have a ranking, right? And if we compare them with other reasoning benchmark, such as math and code, we actually can see some pretty interesting results. So we collect 8 models on 20 benchmarks. Each benchmark, then you have an 8 model ranking. You compare these rankings with other benchmark, you can calculate the Spearman correlation. And this way, the benchmark can be represented as a vector of model ranking. Each benchmark can be represented as a vector of model ranking, and you can calculate the Spearman correlation. You can see all the games, if you look up here, right here, Sokoban Tetris 2048, they have a strong correlation with puzzle-solving games. This is expected because, so puzzle-solving game, more explicitly, I'm referring to these two. So you can see you have Enigma Eval and NYT connections, those puzzle-solving benchmarks, because for those benchmarks that evaluate their distribution are more similar to the gaming environments. And some other interesting observation is for Sokoban. Let's take Sokoban as an example. You can see it also have a pretty strong correlation with some of the math and coding benchmark, with live code bench coding as an only exception. For left bench coding, the ranking is pretty different, somewhat different from the gaming ones. And we also want to study how individual capability contribute to gaming performance, right? So basically, after looking at this, we can see very clearly gaming performance are actually a composition of different types of capability. If we put together the coding capability, math capability, spatial reasoning capability, like puzzle solving, you can see it actually correlates to quite a few benchmarks. So we can regard gaming performance more of a composition of existing capability people care about.
Lanxiang, I just had a question. Like, at least like which games have you found most correlated? Like, for instance, like I've seen a lot of like my friends who are like very good factorial players tend to be like very good programmers, and I'm sort of wondering if you notice like any sort of like peculiarly large correlations that you found interesting.
Yeah. So I think the example I just mentioned, Sokoban, is definitely very correlated. It required a lot of long horizon planning, and so the visual novel game, the Ace Attorneys, very related to language benchmarks, right? The darkest one shown here, it's the live code bench language. So that's very sensible. And for Sokoban, it's very related to math. And for 2048, relatively, it's also so math are also more important. Yeah. So that's just by looking at the correlation matrix, and we have another way of studying this. Yeah, after going to the next slide, we can talk more about how we, yeah, what's the takeaway. So we break down the capability into several categories. We have physics category where we use AMA physics, bench. Also math categories, we use those commonly used benchmark, AME 25, of course, Math 500, like bench math, and also code benchmark, MBC, and the vision benchmark, Vista, language benchmarks. So an interesting question is, what if we can, is it possible to learn a polynomial or linear model that can predict gaming performance based on existing benchmark or a ranking from an existing benchmark? If it's possible, then we can learn a set of model weights, right, that contribute to each set of capabilities. And this provides insight into what perform good on different games means. And after doing this kind of categorizations, we actually learn a linear models with the data we have from across all those evaluations. We see, interestingly, Sokoban Tetris 2048, they are all very correlated with math and coding. And the correlation are actually, especially for Sokoban and Tetris, you can see the R value is very strong, as shows a strong linear correlation. And for Ace Attorney, of course, it's related to language. For Super Mario and Candy Crush, they're very related to spatial reasoning and the physics benchmark. And I think this is pretty interesting because for Super Mario Bros., it requires a good physical sense about controlling the character, doing certain type of actions for certain times. It basically it's kind of a simulation of real world physics. For Candy Crush, it requires spatial reasoning, and it's also what is important, like one aspect reflected in the physics benchmark. So those analyses, they're more of looking into what gaming performance mean in relationship with other existing benchmark. And we also employ other technique to study the implication behind using gaming environments. That's what we call like more of training-oriented analysis. So we train models on Sokoban and Tetris to see how well their performance are able to generalize across different games. Across different other types of tasks. So what we do here is, because the reward from gaming environments, they're discrete numbers, right? So in order to do model updates on discrete numbers, on sparse rewards, we use policy gradients, we use multi-turn RL. So it's very simple. We concatenate the state response reward from each turn into a super long sequence, and we calculate the total rewards for each rollout. And basically, a positive reward will mean you're making progress in this game, or you succeeded. On the other hand, if you have been playing the game over and over again with many turns but no progress, it corresponds to a penalty. So the penalty accumulates, basically. So a small penalty is applied after each action is taken. And the response, the format is, of course, like common to all those reasoning model. We have first the reasoning trait sections, the thinking sections, and also the action sections, where you can take a sequence of actions. And we train the model. The model we used for training is Quan 2.57 billion instruct. We train the model with max number of 20 steps, best side 32, and some other hyperparameters. Another important thing to mention is we are only training on LLMs, not VLMs. In other words, the game states are only textual tabular representation. This ASIC representation you can see from here. We're not doing any VLM training yet. Okay, so after training them on Sokoban and Tetris, the first thing we want to see if the model performance able to generalize within the game, right? In other words, what's the in-domain generalization and out-of-domain generalization? On the second column, on the second row, you can see for the model trained on Sokoban, it not only the biggest performance is, of course, the Sokoban performance on the 6x6 environment, which is the one it's trained on. It has a significant boost from about 11% success rate to 24% success rate. And it also generalized to harder Sokoban with 8x8 grid size, improved around 3%. And you can see, actually, interestingly, also the performance also generalized to Tetris. So in other words, the model isn't trained on Tetris. It's only trained on Sokoban. But you also see a performance boost in Tetris as well, especially the easier Tetris variant, the one type, where you only have one Tetris piece. Because, yeah, all those models, actually, they're pretty poor on those kind of games. That the environments are harder than we thought. So they can only play like basically one Tetris piece type game or two Tetris piece type game. And another generalization we see is on planning task. So this Blocks World. Blocks World is also a kind of a game simulation where you have different blocks and you have a certain task. You need to arrange your blocks in the correct way to finish to achieve the goal. And we see, like, basically on games, it's able to generalize not only within the game but also on other games. Not only on the game, the game it was trained, but also on other games, and also planning tasks that are very similar to games. However, for math and coding, the improvement, we didn't see a clear improvement. So there's a small performance degradation, not a huge degradation, but there isn't a performance improvement. For other agentic tasks like agentic web shop, it does improve the multi-turn interaction capabilities, and the performance improvement is actually pretty significant, right? For web shop, success rate improves from 7% to 20%, around 19%, around 20%. And okay, and then another question we think of is, so we train the models on single type of environment. What if we would scale up the environment type? What if we include not only just one games, but multiple games? What if we include math data into the reason? So each batch as well. What if we do this kind of data mixing? Is the model able to generalize better? So we found that if we train on this kind of data mix, the performance on all benchmark improves, but not as good as training on a single environment. In other words, if we train on math and Tetris, if we train on GSM-AK and Tetris, performance on both GSM-AK and Tetris improve, but its upper bound is not as good as training solely on GSM-AK. So I think that's still a challenge that we're currently studying. We're currently trying to see how well scaling different types of environment could help, whether there's a good data recipe that brings a good generalization across all different settings. Another interesting observation I want to share is here in this experiment, we actually explicitly removed this thinking format because Qwen 2.57 billion, the vanilla model doesn't come with reasoning style, right? So when we're doing this kind of training, there are actually two things it learns. The first one is its performance, the reward it's trained on. The second one is actually its format, right? So so we actually found if we train the models on this format, its initial performance is a lot worse. You can see a very significant performance improvement. The improvement is there, but the initial results is so basically it will have a performance degradation first because the format is out of distribution. You got to learn the format first. We suspect the improvement isn't caused by the model is actually learning something new, but actually just picking up the format. So all those experiments I show in this table, they conducted without the thinking token, the thinking tag. Yeah, okay, so this is what this slide is trying to present. So adding a thinking token leads to a very significant performance difference even before the training. So you can see before the thinking tokens are applied, um, before the thinking tokens are applied um, on Sokoban, the performance is around 20%, right? So without the think tag, its performance is higher. It's on the second column. It's on the one where um, we have a we cross out the thinking format one, so it's 21.1. But if we apply the thinking formats, it's actually 11.3. It's actually a lot worse, because this thinking tag is just out of distribution format for the models. So after training, you can see even on math and coding, the performance still improved, but we're suspecting it's more of um, learning the thinking format. To mitigate this issue, the experiment we're thinking about is we first do a soft fine tuning on the thinking data, then run RL. This way, it first learn the format, then it learns the actual rewards. So this is our next to do. Okay, so another bonus interesting evaluation I want to talk about is Pokemon Red. So in some of the latest model technical report, like Cloud 3.7, Cloud 4, and Gemini 2.5 Pro, you see they all evaluate on Pokemon. But is it really a good eval? I think the short answer for us is no. This is because the Pokemon Red we found, it mostly involves 3 tasks. And all the 3 tasks, they have their own problems. So the first big component is battle control. The battle control only involves in navigating your cursor to and to take different actions, to use different capabilities. But this is too easy. And the second task is navigation. But navigation is actually too hard. This is exactly the question we just discussed. Spatial reasoning, models vision perception capability are still too limited. So interesting thing is when people evaluate the models on Pokemon Red, they print out this grid, right? They overlay a very explicit grid to your Pokemon game. It tells the model whether each tile is passable and what is the coordinate for each tile. What's the property for each tile? Whether the tile will tunnel you to a different place or not. And the third task is long horizon planning for building a strong Pokemon team. But this one is super costly. You can see the first checkpoint in Gemini 2.5's technical report is to reach this Oaks Lab. So basically where you pick up your first Pokemon. And both O3 model and 2.5 Flash, they spend 1,000 steps just to reach the first checkpoints. And the costs are huge. They amount to $50 to $120. And also take a lot of time because we're using reasoning models to generate actions, right? So one interesting aspect we're thinking is instead of just letting the model take very low level actions, we might an alternative way is we ask model to call some tools, say an A-star tool. If we provide it with an A-star tool, so every time the model won't just be taking like a step moving upward, leftward, downward, you can just call this tool and you can find a path to a specific location, to the next level, to the next location the model wants to go to. The number of steps then can drastically reduced. And in that setting, the evaluation target is actually models 2 using capability. So that's another aspect we want to look at moving forward. Okay, to draw a conclusion, gaming environments offer a very rich set of assets. So basically can serve as a good test bed for evaluating and training AI agents, more specific LM-based agents. And with gaming harness and our mitigation strategy, we provide some. We look into some current limitation of the model behavior, and LLM Game Bench reviews the strengths of LLM limitations, strengths and limitations of LLMs. And we also used a training-free and a training-oriented method to study what gaming performance actually means. And currently, we're also working on finding a new training recipe for a training recipe that train on gaming environments with a good generalization. Yep. So I think that's it. Do you have any questions?
Very cool. Yes, thank you, Lanxiang. Yeah, so if folks have any questions in the chat, please go ahead. Otherwise, I had a couple. So I was wondering, like, if we think about like sort of the more on the perf side of things, like at least like when I'm playing video games, like I'm rarely thinking move by move. Like at least within strategy games, there's this idea of like macro and micro, where you like have some sort of high level plan and then you sort of like automatically execute it. Is this like something like people are like experimenting with, like basically having like an LLM like batch, like a long series of actions and only revisit it when it needs to, kind of like system one, system two?
I see. Yeah, I think that's a very good point. I think Gemini actually has this integrated. So let's also take Pokemon as an example, right? So they actually have they actually provide A-star search as a tool they can use. So the LM is more of generating a high-level planning about where the model should go, what's the coordinate that the model should go to the next. If you provide it with a map, the LM is just to make a high-level decision which coordinate I should go, like which house I should go to the next, right? It's no longer needed. It doesn't need to do like very low-level action taking. It just needs to say, okay, go to house one, and then I call this A-star search. It provides a path. So I think that's what people starts to work on, and I think this brings a new aspect of evaluating models to using capability, to calling capabilities. Yeah, I think it's emerging directions, and I think it makes sense to me as well.
Yeah, and I guess like one example where maybe this is not too relevant is the like Phoenix Wright game, where it's like basically effectively turn-based, and which actually, like, one of my first thoughts was like, well, if you're looking at a game like Phoenix Wright, well, it's not like I don't think that those games are necessarily like open, as in like you can't like mod them to turn them into an RL environment. And so like how do you typically recommend people basically turn their favorite video game and add it to like a gaming LLM gaming benchmarking suite?
I think first, yeah, I agree. It depends a lot of so we recycle a lot of the existing assets, existing infrastructure, say OpenAI built for their stable retro, where as long as you have usually a read-only memory file for the games, you can have an emulator, right? Where you can if you provide it with different random seed, it generates slightly different games. So I think all those kind of emulators are there. If you want to add your own custom game, it just requires more engineering. So I would recommend, if you're interested, start out with the games that are already well supported. Yeah.
All right.
For the Acetone example, it's yeah, I agree. It's extremely hard to hack. It took us quite some time to figure out, in the read-only memory file, different memory address corresponds to different game status, right?
I see. Were you guys using Game Cheat for this? Like, I think there was like that was the one piece of software I'd used in the past to like understand like a specific location on the screen, like what, like let's say a score, what like address of memory does this map to?
Oh, we're just using stable retro. Stable
retro again. I see.
Yeah.
Okay.
Stable retro, they have this emulator, right? And we basically just do a manual inspection, like do an inspection ourselves. What different memory address could be, what fields are in different memory address.
Okay, and then I guess I have two more questions, which is so regarding like harnesses, like I'm sort of like, maybe this is I guess I'm just wondering for your opinion, which is that like how much of a harness would you consider to be cheating? Can LLMs build their own harness? How do you think about like, just again, like the bitter lesson for gaming, really?
Yeah, I think that should evolve over time. My opinion is, at the end of the day, we won't need harness. Harness is just a temporary solution. At the end of the day, if we believe AI can be strong enough, they shouldn't be there. So we build harness only for the sake of distinguished LM capability at this moment. So we employ as minimal gaming harness as possible, and we want to run statistical tests just to make sure we provide harness to a degree that can distinguish model, and that's it. That's why we don't think Pokemon Red is a good evaluation, because the harness is just too much. It's more of evaluating harness instead of evaluating your engineering, right? Like Cloud doesn't have as good a harness versus Gemini. So I think it's more of evaluating harness than the model itself. Yeah.
Interesting. All right, and I guess like my last question is that like games are obviously very broad. Like for instance, like um, when I think of like the early sort of like OpenAI like era of AI, like the OpenAI 5, like with the Dota bots and the DeepMinds, like StarCraft bots, like basically, I think a common critique then was that like uh, getting good performance on games like doesn't really matter because um, like it doesn't correlate to like other tasks. But like I know you sort of talk about correlations briefly, but maybe my question here is that like there are like some forms of video games that are commercially useful. Like for example, like if you think of games like I don't know, given $100, make as much money as possible, or like be the best in the Kaggle leaderboards. Is this like a direction you're exploring, and why or why not? Really love to hear more.
Yeah, that's a great question. I think there are a lot of, say, economic simulation games, strategic
Yeah.
games that have real world, potentially real world use case, right? They're more relevant to our, I would say, I don't know, maybe decision making in business
Mhm.
scenarios, or like more of game theoretic games.
Mhm.
I think those are also very interesting, and we're definitely looking into it. So currently, we're actually doing multi-agent evaluation. In other words, um, like so let's say Monopoly, right? In those kind of games, you have a lot of competition and also like game theory based reasoning going on there, or Catan, or this meta diplomacy games. All those games where I think it's a big future direction for us. Yeah.
Mhm. Yeah, like I guess what's interesting about Monopoly is like I've heard anecdotally the best strategy is you just buy everything you come across. Like that's I think the sort of like optimal strategy. So then I guess like it's easier to measure if you're doing well or not.
Mhm.
Okay. Um, cool. Like, well, thank you so much, Sunshine, for coming on. And folks, if folks have more questions to him, like after this talk, I think he's on the Discord already. So thank you for joining.
Yep.
Starting next week, folks, like we have a long series on distributed computing happening, like with 4 different talks. So this is if you're curious about multi-GPU programming, like we're hoping to create like a nice accessible intro there. So thank you for joining today, and see everyone next week.
All right. Thanks so much. Bye.
Thank you.